Listen to the fans on a 15-watt laptop pushed into severe thermal throttling. This is our baseline constraint, the potato hardware. We ran the same benchmark suite across two very different environments. On one side, that struggling 15-watt laptop. On the other side, a clean cloud reference runner pinned to BatPak version 0.10.0. This chart plots the output of both machines. We have higher y-axis values for the faster cloud environment and lower values for the laptop. But look at the lines. Their peaks, valleys, batching curves, and performance cliffs appear in the same places. When the same performance shape emerges across extreme hardware disparities, you are looking at a predictable, coherent software architecture. This is BatPak. It is an embedded, sync-first event store written in Rust. It is not a general-purpose database, and it deliberately avoids a server process and a required asynchronous runtime. BatPak enforces a strict boundary for local truth, and every accepted write returns a structured, verifiable receipt. Evaluating BatPak means analyzing the structural cost of recording, verifying, replaying, and durably preserving that receipt-back truth rather than just pointing at top-end speed. First, we look at read performance. We are operating at the nanosecond scale, 289/356. Dispatch frames measure in the sub-microseconds across operating systems. Queries in this suite happen in microseconds. This diagram shows a fan-out operation, pushing data to multiple subscribers at once. Notice the nearly flat scaling curve. In this benchmark, pushing to 100 subscribers added only a few percent over pushing to 1. Even on the Potato laptop, the fan-out shape stayed stable. When rebuilding state, what BatPak calls projection replay, that throttled hardware processed about 2.5 million events per second. Reading, replaying, and moving established truth through the system is extremely fast in these tests. The dominant cost appears when establishing durable truth in the first place. Write performance drops the moment data must cross the physical storage boundary. Single durable writes carry a severe time penalty. On the Windows runner, those delays stretch into multiple seconds. This is where fsync enters the picture. Fsync is the operating system call that asks the storage stack to make data durable. BatPak does not advance the durable frontier until that boundary is crossed. This chart visualizes the cumulative cost of forcing the system through 100 individual fsync operations sequentially. The time stacks into a massive bottleneck. The architectural response is batching. By grouping commits, you amortize the physical cost of hitting the fsync wall. Single force commits are slow. In one Linux benchmark, grouping 100 writes cut the path from roughly 599 milliseconds to about 18. BatPak honors the inescapable physics of disk durability instead of pretending they disappeared, and its batching machinery turns that fixed toll into useful throughput. The systems audit also surfaces explicitly measured structural bottlenecks. This radar chart maps performance across different data layouts. You can see a specific 20x performance drop when shifting from a local layout to scan-oriented array of structs paths. There is also a strict cold start penalty. Loading 1 million events from a checkpoint on Linux takes 8.4 seconds. Because these cliffs are measured, reproduced, and documented, they become roadmap targets instead of hidden surprises. Some benchmark setups can blur durability costs by moving acknowledgement or flush work into the background. BatPak chooses to keep that boundary visible. Strict hardware predictability demands software honesty. BatPak forces developers to face and engineer around the real physical cost of maintaining a bounded local truth boundary.